All scientific research is an outgrowth of our insatiable desire to know things. We all want to know things about the natural world, and as we saw in the last lecture, science is the best way to discover how the physical universe works. This process of discovery employs the scientific method, which may be idealized as a cyclic process of inquiry based on observations, synthesis, hypothesis, and predictions that lead to more observations. Too often, science educators focus on the most firmly established scientific answers, and in the process, this dynamic process, the creative process of asking questions, is sometimes shortchanged. In the last lecture, I told you about the National Science Education Standards, which call for science education reform centered on the idea of science as a process of inquiry. This lecture, the second in our series, therefore focuses on questions. I have two objectives in this lecture. First, I want to consider the surprising nature of scientific questions themselves. Then I'm going to tell you about the scientific method by which scientists attempt to answer questions about the natural world. To begin with, I want to tell you about 6 different aspects of scientific questions. And the first of these is that many important questions are absolutely beyond the realm of science. Science cannot tell you the meaning of life. It can't tell you who to marry. It can't tell you whether to have children. It can't tell you if God exists. So you see, science addresses only those questions that can be answered by reproducible observations, by controlled experiments, by theory, guided by mathematical logic. Economist and philosopher Kenneth Boulding has said, quote, "Science is the art of substituting unimportant questions which can be answered for important questions which cannot." Well, Boulding may have been speaking only half in jest, but it's certainly true that science can answer many of those important questions. Nevertheless, science informs many of the important non-scientific questions in our lives, including choices about health, about work, about relationships. In your decision to have children, you may want to know something about your family histories of genetic diseases, for example. Even if you want to know about the meaning of life and the existence of God, you need to understand the nature of the physical universe in which we exist. And that's something science can do for you. Of course, there are also many questions that are scientific, and that leads to my second point, the second point about scientific questions. Scientific questions are richly varied in scope and in content. Scientific inquiry is diverse as the natural world itself, but most scientific questions fall into 4 broad categories, and I want to tell you about these 4 categories of scientific questions. We have existence questions, origin questions, process questions, and finally applied questions. The existence questions ask what objects and what phenomenon occur in the natural world. This has been a passion of scientists for hundreds of years. Scientific explorers of past centuries reveled in voyaging to exotic lands in pursuit of animals and plants, of mineral specimens and fossils. Charles Darwin cut his scientific eye teeth as a naturalist in the Voyage of the Beagle. Chemists isolated element after element. Physicians dissected diseased corpses. You had astronomers cataloging stars and physicists that scrutinized the unusual phenomenon associated with electricity and magnetism. We have continuing research of this kind today. Many scientists are now cataloging galaxies. They're sequencing genomes. They're isolating different kinds of viruses. They're finding new planets all the time, unearthing new dinosaurs, and eavesdropping on extraterrestrial life. The second kind of questions are origin questions. These explore how natural objects and phenomenon came to be. Questions about the origin of the universe, the origin of the earth, and the origin of life itself are among the most fascinating mysteries in science. They have to be answered with a plausible sequence of historical events. They have to be deduced from contemporary evidence, and they have to be constrained by natural laws. These are wonderful questions to sink your teeth into. And then we have process questions, questions that ask how nature works, These questions are often closely linked to inquiries about origins. They explore how stars evolve, how rocks erode, for example. You can ask how cancer develops, how atoms interact with each other, how fungi reproduce. These are all kinds of process questions. Descriptions of the dynamic interplay and evolution of natural systems helps us understand the past and the present, and also may help us to predict what's going to happen in the future of these natural systems. And then we come to the fourth kind of question, applied questions. These look for ways to manipulate the physical universe to our advantage. Curing disease, devising new materials, modifying the environment are all aspects of applied scientific questions. Such questions are often quite specific. They're often rooted in technology, the search for safer cars, for example, for cleaner energy sources, cheaper fuels, longer lives. These are all applied questions that many scientists are tackling today. These pursuits, of course, are also closely tied to other kinds of scientific questions. You can't manipulate nature without first understanding it. Curing infectious disease, for example, that requires a knowledge of infectious organisms, what are out there, how they behave, why they behave the way they do. And of course, constructing skyscrapers involves understanding the properties of materials, a detailed knowledge of how these materials behave under various stresses. Now, to a third aspect of scientific questions. That is that old questions, when they're answered, often lead to a whole new set of questions. In 1843, the art critic John Ruskin lamented that to know anything well involves a profound sense of ignorance. This sentiment strikes a very responsive chord in most scientists today. The more our knowledge grows, you see, the more we realize how much we don't know. There have been many unanticipated discoveries like X-rays, tectonic plates, which I'll tell you about, the genetic code, buckyballs. All of these discoveries opened up vast new areas of research. Rather than answering a question, you really just open the door on whole new regimes. The answer to existence questions invariably leads to questions about process and origin. For example, if we were to discover extraterrestrial life, it would not only tell us that those life forms existed, but it would open up huge areas of research about exobiology, which we can't even conceive of right now. My fourth point about scientific questions is that these questions are often interconnected in surprising ways. As scientists explore the most sweeping unanswered questions, they often discover links between what at first seem to be very unrelated topics. Big questions really then tend to blur the traditional boundaries of science departments. They unify our view of the natural world. Let me give you some examples. Plate tectonics. Plate tectonics was a revolution in the Earth science, which showed how the dynamic interior of the Earth bears directly on our understanding of what's happening at the surface. But it goes beyond that. Plate tectonics also provided profound information about life's origin and its evolution. Then we have studies of ancient mass extinctions. These studies provide models for understanding the importance of today's global environment and may help us answer many of the questions that we have about what humans are now doing to the environment, even though we're looking at environments in the globe millions or hundreds of millions of years ago. Scientific questions are also often linked by their philosophical approach. For example, we have reductionism, which provides one approach to answering questions. It's based on an assumption that physical systems can be understood by looking at the smallest building blocks, the smallest units. You can understand materials by looking at atoms. You can understand people by looking at their genes. Particle physicists' search for the theory of everything, which I'll talk about in a later lecture, is another example of this, looking for the finest structure of matter, even below the scale of the atoms, below the scale of the atomic nucleus, and from that, trying to understand the entire physical universe. That's an example of reductionism. At the extreme opposite, you have ecosystems, you have the brain, the universe as a whole, and these are vast systems that have to be studied in their collective whole as unity. It turns out that many of these large, complex systems display behavior that you could never predict just on the basis of the individual components. You see what are called emergent properties. From atoms, you get planets. From planets, you get life. From life, there emerges consciousness. And at each stage, you'd never predict that emergent property from the previous set of starting materials. A fifth aspect of scientific questions is that some questions are not now scientific, but someday they may become so. Let me give you an example from history. In 1900, before Edwin Hubble's discovery of the galaxies, questions about the origin of the universe were not in the realm of science. They were pure philosophical speculation, because there's no observation you could make about the universe that would tell you anything about its origin. Nobody had thought of a kind of observation that would help. But when Hubble discovered distant galaxies and discovered that they were moving away from us, it opened this whole new realm of questioning about the origin of the universe, and we'll see that in a later lecture. Today, the study of human consciousness is probably beyond science as well. We don't even have a good operational definition of consciousness. We don't know how to quantify it. We don't know how to define it. We certainly don't know how to study consciousness as any physical entity. But that situation may change. After all, many people are studying the brain, studying the behavior of neural systems. And so someday, as we understand more and more, the question of what is consciousness may fall into the scientific realm. Now to my sixth and last point about scientific questions. And that is that most questions can't be answered completely. This is a great frustration to science. There are at least 4 factors that prevent us from obtaining complete answers to many of our scientific questions. Let me tell you about these 4 factors. The first is a common one that you've all heard of, and that's experimental error. All measurements, no matter how accurate, no matter how carefully done, contain some error. Think, for example, about measuring the thermal expansion of a metal bar. If you heat up a piece of metal, a bar, for example, that's about 3 feet long, it's going to get a little bit larger. And thermal expansion is an exact measurement of how much longer the bar gets with temperature. Well, you can measure thermal expansion. You can measure the length of the bar, and you can measure temperature. And so you can have a plot, temperature versus length, and that tells you thermal expansion. But no matter how carefully you do those measurements, there's always going to be some error in the measurement of temperature. No matter how well you design your thermometer, there's going to be some uncertainty. And there's also going to be some uncertainty in the length. Maybe you can measure that length to 1,000th of an inch, but can you measure it to 1,000,000th of an inch? If you can measure it to 1,000,000th of an inch, can you really measure it to 1,000,000,000th or 1,000,000,000th of an inch or more? There's always going to be some degree of error. There's always room for improvement in scientific experiments. And so the scientific process is never ending, and some questions can never be completely answered. Now, science is a never-ending process because new techniques for making these measurements are constantly being invented. So we can always improve the precision and the accuracy with which we make our observations and measurements. We have bigger telescopes. We have faster electronics. We have more sensitive analytical methods, for example. This regularly improves our ability to make measurements, but we're never going to reach the end of that road. There's always room for improvement. A second reason why scientific questions can't be answered is called the uncertainty principle. And this applies to the subatomic scale. At that scale, every measurement that you can conceive of making alters the thing that's being measured. This is one of the most unsettling discoveries of quantum mechanics, because it turns out at nature's smallest scale, at the scale of the electron, the scale of the atom, everything that you can use to measure atoms and electrons has comparable energy to the atoms and electrons you're trying to measure. It's sort of like trying to determine if there's a bowling ball in a room, which is dark, and the only way you can try to find the bowling ball is by rolling other bowling balls into the room and listening for a clunk. But as soon as you hear that clunk, the bowling ball has moved its position and you don't know where it is anymore. And that's sort of what happens at the subatomic scale. The uncertainty principle is another reason why anything you measure is going to change, so we can't know everything there is to know about the physical universe. Chaos is a third problem. Many natural systems are chaotic and thus inherently unpredictable. We believe that there's an orderly universe. We believe in natural laws in which a given set of initial conditions leads to a predictable outcome. But the trouble is, these chaotic systems are such that the slightest change in initial conditions someplace down the road can affect the systems and their behavior drastically. One of the ways this is described metaphorically is called the butterfly effect. The idea that a butterfly flapping its wings in Asia can change the weather pattern over North America several months later. So even if an entire physical system obeys all the physical laws, and even if we can codify all those physical laws, we can never measure the initial state of a system with such precision and accuracy that we can predict how it's going to become if the system is chaotic. So that's another inherent limitation on knowing how the universe is going to behave. And a fourth, and I guess a rather prosaic limitation on what we can know, is the speed of light. To the best of our knowledge, the fastest anything can travel, any physical object can travel, is just under about 186,000 miles per second. And that means there's some places in the universe we're never going to be able to go. They're distant objects for which we cannot possibly know what's happening to them today. We can only see them because they're far away, as they were in the past. It also means that we can never travel backwards in time, at least with present technologies and present understanding of the physical universe. And these are other limitations on what we can know. But I have to say, in spite of these and other inherent limitations into the natural world, the methods of science absolutely, positively provide the most effective, the most powerful tool that we have for understanding and for modifying the physical world. I now want to change gears. I want to tell you about the scientific method. This is a systematic process which scientists have developed to discover principles of the natural world. Now, don't get me wrong, the scientific method is a complex, it's a variable process, it's a human process. It differs in detail from scientist to scientist, from discovery to discovery. It's very hard to give you a simple overview of the scientific method. And one of the things I want you to get out of this lecture series is how richly varied the discovery process can be. But having said that, it is possible to idealize the process of scientific discovery into a simple four-step cycle. And these steps are observation, synthesis, hypothesis, and prediction. And the predictions then always lead to new observations, so the cycle goes on and on. The first step in most scientific studies is the collection of data. This includes observations, it can include measurements, it can be experiments of various sorts, and these data have to be tabulated. They have to be expanded into monographic studies of all the different kinds of objects or all the different kinds of phenomena that are out there. They can be collected specifically to test a prediction, but primarily you're just going out there and seeing what's out there. This is related to those existence questions I was telling you about. And many, many of the scientific texts that you've seen relate to this sort of effort. For example, you might want to describe all the different bird species in a particular area. And so eventually you bring these bird species together and you'd have books that show lots and lots of species. You've seen these, they're available to amateur bird watchers, but this is an essential part of the scientific effort, to catalog all the different kinds of species. One of my very favorite books of this sort, because my wife and I love to collect fossils, is a book that describes all the known trilobite species. And this is a Bible for people who are involved in the paleontological study of trilobites. Page after page after page of all the known varieties of trilobites. These are ancient fossil animals that lived more than 300 million years ago. So that's the first step, collecting data. Now sometimes these data are going to be tabulated in huge volumes of numbers. For example, I told you about thermal expansion before. You can have table upon table of thermal expansion coefficients for all different kinds of materials. That information is vital both for engineers who are trying to build structures like buildings and bridges, but also for scientists trying to understand the properties of materials. And these tabulations, these volumes of numbers, are an essential part of science. They're the first step in that scientific method. The second step is the recognition of patterns, the search for what I call symmetries. Most scientists have a deeply held belief that there are regularities, that there are patterns in the universe, and we can find those patterns. The recognition of a pattern in nature from vast amounts of data, that's the art of science. Sometimes this step involves recognizing similarities among seemingly different phenomena, such as different forms of electricity. Indeed, one of the great discoveries in the 19th century was that lightning and static electricity and the kind of electricity produced by electric eels and the kind of electricity produced in batteries are all one and the same phenomenon. Recognizing these very different physical phenomena as being one sort of thing. That's a process of synthesis. Sometimes the stuff's mathematical in nature, finding all sorts of disparate data and realizing that they all fit one simple equation. And I'll talk to you about Johannes Kepler and how he recognized that the orbits of planets fit this kind of mathematical relationship, a form called an ellipse. And that was another great discovery. Now, the third process, once a pattern is found, the scientist is going to propose a possible explanation in the form of a hypothesis. Now, often this step is just as straightforward as generalizing the synthesis. Kepler saw one planetary path was an ellipse, and he made a generalization that all planetary paths are ellipses. You see that two types of electricity are the same, and then you say all types of electricity are the same, and so forth. Once a hypothesis is well tested, once it's examined by many, many people and seems to fit all the observations, it may assume the status of a natural law, that is, if it's mathematical in form, or perhaps a theory if it's more descriptive in nature, as in Darwin's theory of evolution by natural selection. A key point about scientific theories and hypotheses. Any scientific hypothesis or theory must lead to unambiguous predictions. They have to be testable predictions. They require a new round of observation. If you propose a theory and there's no way to test it, then it's beyond the range of science. Consequently, a scientific theory can always be disproved. If you make a prediction and that prediction is unfulfilled, then your theory is wrong, or at least the theory has to be modified. You can never completely prove a scientific theory, a scientific law, because there always is some measurement yet to be made that's a prediction of that theory. Science is therefore extremely vulnerable to attack. A single odd fact has the potential to undermine a long-standing theory. Each counterexample has to be laboriously scrutinized. You have to go into the laboratory and say, why does this example not seem to fit that theory? And this is why supporters of evolution often find themselves on the defensive when they're debating creationists. Creationists say evolution did not occur. And they can show individual examples of rocks that may seem to violate the concept of evolution. For example, they might show you a rock with limestone and fossils that are supposedly hundreds of millions of years old, and yet they have human footprints in the same rock. Well, that would violate any idea of the theory of evolution of humans being much more recent than the hundreds of millions of years old rock. So each such anomaly then has to be analyzed and scrutinized. It's very difficult to argue against such evidence in a 2-hour debate. You need years and years to analyze this sort of data. There actually is one more part to this 4-part cycle, and that's right at the center. That's the idealized cycle always has to have a paradigm in the middle. The paradigm is the prevailing system of expectation. It's the prevailing ideas about how the natural world works. Because every observation, every prediction, every hypothesis is made in the context of our present understanding of the natural world. So underlying all of this human process of the scientific method, there always is an underlying paradigm. We wouldn't ask questions about life on other worlds, for example, if we thought that life on Earth is a unique phenomenon. If that was part of our built-in belief structure, you just wouldn't think about life on other worlds. And I'll bet you that there are many important and interesting questions that scientists could ask that they're not asking right now just because it doesn't fit into our current paradigm. Paradigms therefore gradually shift, and the questions scientists ask also shift. I should tell you right up front that the scientific method is rarely followed as an exact cycle. Human imagination, intuition, chance are vital elements of this process, and we're going to explore some of those variables in the next lecture. But first, I want to give you a historical example which is often cited as the epitome of the scientific method at work, and that's Dmitri Mendeleev's discovery of the periodic table of the elements. Mendeleev had data on 63 different elements. That was his input. Those were his observations. That was enough to begin to see patterns. He expected that he was going to find order in this collection because he believed you couldn't have 63 independent and separate fundamental units of matter. He thought there had to be some underlying order, and so he looked for it. That was his paradigm. He ordered the elements from left to right according to their weight. He ordered them in vertical columns when he saw elements that had very similar behavior. And so he built up this table, and everything seemed to fit. Furthermore, the table that resulted had a few gaps in it. places where it seemed like elements were missing. So he predicted that those elements would be found. And sure enough, within a decade after he predicted the table, they actually found some of those elements that were missing. That's, in a nutshell, how this whole scientific process works. Now, the Mendeleev story is compelling, but science doesn't always work quite in such a linear fashion. Often there are anomalies that lead to new insights. Historian of science Evelyn Fox Keller has observed, and this is a quote, "When scientists set out to understand a new principle of order, one of the first things they do is look for events that disturb that order. Almost invariably, it is in the exceptions that they discover the rule." When anomalies are found that violate well-tested theories and laws, it usually means that the old theory or law is valid, but it's just a special case of a more general law. And let me show you what I mean. An everyday example would be provided by the hypothesis that all objects fall under the force of gravity. And I can show you this. I can take an object and drop it, and it falls. I can take another kind of object and drop it, and it falls. Another object and drop. I could do this all day long. I could take objects and drop them, and they fall. It's something that's a part of everyday experience. And so you develop a hypothesis that when objects are dropped, they fall. And then, in your process of studying the universe with a great deal of care and precision, you finally drop a helium-filled balloon. And it doesn't fall. Well, what does this mean? How do you accommodate this into your theory? It doesn't mean that the idea when objects drop that they fall is wrong. It means that the falling objects are part of a more general theory. Indeed, it's Newton's theory of gravity, which explains both the objects that fall down and the objects that fall up. And then if you look in more detail about how things fall, you find that Newton's laws are only a special case of Einstein's more general relativity, in which objects that are moving very fast or are very massive behave differently than the kind of objects we have in our everyday world. So the classic laws of motion fail under conditions of extreme speeds, extreme masses, and so forth. And so you keep having to have more general laws that subsume the more familiar everyday kind of experience that we have. Geneticist Barbara McClintock underscored this point in her Nobel Prize-winning work on corn genetics. Other workers at the time believed that a simple relationship existed between individual genes, which are passed down from parents to offspring. Genes that determine the characteristics of individual corn kernels. They sort of thought of the master gene, a gene controlled the trait. Well, McClintock thought differently. She saw the kernels in a different way. She said, see that one kernel that was different in your corn. And you've got to make that kernel understandable. And when you see the one kernel that's different and understand that, then you find the truth about genetics. In the process, McClintock was able to find that the genes occasionally move. They shift places, they jump, and this provides an additional vitally important mode of genetic variation that no one had seen before. So the scientific method is not a strict guidebook, but rather it's an idealized path to knowledge that often seems to fit better in retrospect as we look back on history than it does while the discoveries are actually being made. Now let me summarize this lecture. First, I considered 6 aspects of scientific questions. First, many important questions are beyond the realm of science. Second, scientific questions are richly varied in scope and in content. Third, answers to old questions often lead to new questions. Fourth, scientific questions are often interconnected in surprising and remarkable ways. Fifth, some questions are not now scientific, but maybe someday as our understanding grows. And sixth, most questions in science can't be answered completely. Then I looked at the idealized 4-step scientific method, which includes first, observation and experiments, that is, collecting data. Second, recognition of patterns in that data. Third, the development of a hypothesis or a theory. And fourth, the predictions which then lead to new observations. This scientific method is an elegant process for learning about the natural world. It's neither intuitive nor obvious, however. In the next lecture, I'm going to chronicle the 5,000-year development of the scientific method.